Hi, it's Ms. Moser, back with just a few notes about some other types of compounds, what they're all about, and how to name them. Just a brief introduction. So far, we've talked about ionic compounds, like our old friend sodium chloride here, and we've talked about molecular compounds, like our friend ammonia, NH3. And if you remember, ionic compounds have very high melting points and boiling points, tend to be solids at room temperature, largely because the forces of attraction stretch in all directions through the material along a very specified grid based on how those ions are arranged. Okay, molecular compounds are more likely to be gases at room temperature, or at very least to have very low melting and boiling points compared to ionics, because while the forces inside the molecules are very, very strong, the forces between one molecule and the next aren't really all that strong. So it doesn't take a whole lot of energy to get them to push past one another. Well, now there's one other kind of compound that we're going to talk about, and it's sort of an interesting, weird hybrid. It's the covalent network compound. So remember, in ionic compounds, each atom has either taken on additional electrons or given up electrons, so they're ions. In molecular compounds, they're sharing their electrons. In a covalent network compound, they are bound together by shared electrons, so they are covalently bound. However, the forces of attraction stretch all the way through the material, kind of like an ionic compound. In the covalent network compounds, there are no individual molecules. The entire mass is held together in a three-dimensional network. So like an ionic compound, there are no distinct units. Because of that, we can't have a molecular formula, even though it's held together with covalent bonds. So the formula indicates the smallest whole number ratio, just like in an ionic compound. But they're named like a molecular compound. You don't need to know a whole lot about this, because when you see something like silicon dioxide or trisilicon tetranitride, you'll know that these are two non-metals, and you'll assume that they're bound covalently. Therefore, you'll automatically revert to the molecular naming rules. So while they're not strictly molecular compounds, they are named like them. Interestingly enough, though, some of these covalent network compounds are fairly important in other ways. They're incredibly strong, again, because those forces run through the materials in all directions. Silicon dioxide is a major component of Earth's crust. Lots and lots of minerals that you've touched every day are made largely of silicon dioxide. There's another one that humans seem to be rather fond of, and it's got some great industrial uses too. It's made of carbon atoms in a covalent network, diamonds. So it's the hardest known substance on Earth. You can't melt it, you can't break it, but boy, you sure can put it on an industrial drill bit and drill through anything. Okay, that's the covalent network compound. Two more types to go. Moving right along. So let's talk about acids. I've got a picture of, nice orange, corrosive, bubbly liquid, which is what everybody thinks of when they think of acids. But really, acids are just a molecular compound, just another type of molecular compound. There are two broad categories of acids. Binary, the prefix bi, meaning, that's right, two. Binary acids only have two elements in them. And oxyacids. Can you imagine what oxyacids might have in them? Yes, oxygen. And acids, interestingly enough, are always aqueous solutions of whatever the substance is. So you cannot have a solid that is an acid. It only becomes an acid once it's put in aqueous solution. A lot of these compounds, when they're not in aqueous solution, exist as gases, actually. There are a lot of acids that are closely related to polyatomic ions. Sulfuric acid is H2SO4, and it sure looks like some hydrogen bound to the sulfate anion. Nitric acid is HNO3, and what you have is hydrogen that has bonded itself covalently to what would have been a nitrate anion. Acids have their own naming conventions, and we will learn those later in the year. But for now, the most common acids, if you pull out that ion reference sheet that you've been given, you'll find a little section down here at the bottom with common acids. Hydrofluoric, hydrochloric, those are binary acids. Nitrous, nitric, acetic, carbonic, sulfuric, chloric, basically the ones that we might reference from time to time. So don't forget they're there. One more thing to go. Salts! They're not what you think, hence the salt shaker. So salts are actually ionic compounds, and most specifically we consider an ionic compound to be a salt when it's composed of a cation and the anion from an acid. So if we take a sodium-containing substance and mix it with hydrochloric acid, which is hydrogen and chlorine, we can generate HCl. That's considered a salt. Salts can be any ionic compound that has a cation and an anion, as long as that anion could have been from an acid. Again, salts are just named as ionic compounds because that's what they are. There are acids that have the anion from the acid along with one or more of the hydrogen atoms, and these typically get the prefix bi. Sometimes you'll see hydrogen added to it. So CO3 is the anion from carbonic acid. It's the carbonate ion. When we leave one of those hydrogens attached, we call it the bicarbonate ion. Okay, that's it. So, nothing else to see here, really nothing to practice. You have a quick recall quiz. Bye-bye.